Hello students. Now in today's session we will discuss some important numericals from chapter Thermochemistry. Usually most of the students feel ease of doing these numericals, but the thing is it depends on the numerical. Usually when a question is given to find out enthalpy change, enthalpy change will be calculated as enthalpy of products minus enthalpy of reactants. This is the usual method. But in the question, if bond dissociation enthalpies are given for reactants and products, then enthalpy change can be calculated as bond dissociation enthalpy of reactants minus products. This point of difference you have to remember, because bond dissociation enthalpy is opposite to bond formation. That's why. Now this is one such model from thermochemistry. It's a very important model. We should be very careful in solving such question. Don't be in a hurry. Okay. First of all, let us write the complete equation for this reduction equation. Suppose propene means CH3, CH double bond CH2 plus H2 giving rise to CH3, CH2, CH3. For this, delta H1 is the enthalpy change given. Okay. Now, how do you express this delta H1? This delta H1 can be expressed as bond enthalpy of reactants minus bond enthalpy of products. What is bond enthalpy of reactants? How many bonds are there? Bond enthalpy of CC single bond plus bond enthalpy of C double bond C plus how many CH bonds are there? 3, 4, 5, 6. 6 times of bond enthalpy of CH bonds plus bond enthalpy of HH single bond. Well, one should be very careful while answering such models. Now this is about delta H1 expression. On simplification, observe anything gets cancelled. This is that of reactants only. Minus, and that of products is how many CC bonds are there? 2 times of bond enthalpy of CC single bond plus 3 plus 3, 6 plus 2, 8 times of bond enthalpy of CH bonds. This is that of products. Now on completing the multiplication with this minus sign, this will be minus and this will be minus. Let us do, because of a space problem here, this become minus. Right? Now cancel the things. 8 CH bond enthalpies and 6 CH. This 6 will be cancelled. Here minus 2 CH bond enthalpies were left. Next, minus 2 CC bond enthalpy and 1 CC bond enthalpy. This will be cancelled and here 1 CC bond enthalpy will be left. Now, what is the final expression? Delta H1 will be expressed as bond enthalpy of C double bond C plus bond enthalpy of H single bond H minus, I am taking minus common, bond enthalpy of CC single bond plus 2 times of bond enthalpy of CH. So this is left after I had taken minus again common, right? Now this is delta H1. See, for our convenience, let us highlight this expression. This is delta H1 expression. Now, what is the next equation? Cyclopropane. CH2, CH2, CH2. Cyclopropane, when subjected to reduction, gives again the same propane, aliphatic propane. This enthalpy change is given as delta H2, which can be calculated as delta H2 equals to how many CC bond energies? Bond energy of CC given 3 times plus how many CH bonds? 6 times of bond energy of CH. This is that of one reactant plus bond energy of another reactant HH. Whole thing comes under reactants minus bond energy of products we have to do. How many? 2 bond energies. 2 into bond bond energy of Cc single bond plus 8 into bond energy of CH single bonds. Okay. Now let us multiply for cancellation. If you multiply this with minus, this also become minus. Minus. Now what are the things that can be cancelled here? 6 CH bonds and 6 will be cancelled, minus 2 CH bonds is left. And then this is 3 CC bonds, 2 CC bonds. This is plus and this is minus, 1 will be left. These two are completely cancelled. Anything else? So this can be expressed as delta H2 can be expressed as CC bond enthalpy plus HH bond enthalpy. Bond enthalpy of CC plus bond enthalpy of HH minus, I am taking back, minus 2 times of bond enthalpy of bond enthalpy of CH bond. So this is the expression for delta H2. See, this one is the expression for delta H2. Now what we are asked to calculate? We are asked to calculate delta H2 minus delta H1 equals to, means this expression minus this expression. So it is bond enthalpy of CC single bond plus bond enthalpy of HH single bond minus 2 times of bond enthalpy of CH. This whole thing comes under delta H2 minus bond enthalpy of C double bond C plus bond enthalpy of H single bond H minus, I am multiplying, bond enthalpy of C single bond C minus 2 times of bond enthalpy of CH, on multiplication with the negative sign. Now see the things that can be cancelled. Now multiply with this minus again. Remove the bracket. This will be minus, this will be minus, this will be plus and this will be plus. So now look at the things that can be cancelled. What are they? HH bond enthalpy plus and minus will be cancelled. 2 times of CH and 2 times of CH plus and minus will be cancelled. And one CC bond enthalpy and another CC bond enthalpy. It is 2 times of CC bond single bond enthalpy minus bond enthalpy of C double bond C. 2 CC bond enthalpy minus C double bond C enthalpy. Which option it is? Second option. See, as I am explaining it to you, it might have taken more time, but in the examination you can, by practicing several such questions, you can solve it in less time. Okay, you have to maintain the time without fail. Let us see another question. See, this is another question, that is molar heat capacity of water which is at equilibrium with ice at constant pressure is 0 or infinity or 40.45 or 75.48. Now let us see which one is the solution, right? See, we have molar heat capacity at constant pressure as delta H by delta T at constant pressure. This is a standard expression from thermodynamics, even chemistry and physics thermodynamics. Now at equilibrium, as they are at equilibrium, temperature will be maintained constant. That's what the condition of equilibrium. All measurable parameters remains unchanged, constant, right? As temperature is constant, change in temperature will be 0. So Cp will be equals to infinity. So simple questions only. They are all simple questions. We should have a good hold on the basic definitions, right? Now let us see one more question. Right, this is another question from thermochemistry, right? Spontaneous adsorption of a gas on solid surface. Spontaneous adsorption, you know that occlusion of a substance on the surface of another substance, right? Spontaneous adsorption of a gas on the solid surface is an exothermic process. Because why it is exothermic means actually on the solid surface, when gas particles are getting adhered, right, as they are getting accumulated, energy release takes place. Then How the reaction is spontaneous means delta G finally should be negative. We studied that. So what's the relation? Delta G equals to delta H minus T delta S. Reaction is observed as spontaneous. So what's happening? The gas molecules which are randomly moving, which are freely moving above the surface, are getting accumulated and adhered, during which their entropy is decreasing. Entropy of the gas is decreasing. Entropy of gas is decreasing. Means final entropy is less than initial entropy. So delta S sign is what? Final entropy is decreasing. No. Final entropy minus initial entropy. Less entropy minus more entropy. So delta S sign is coming as negative sign. Minus of minus, it become plus. So for this to be spontaneous, delta H sign should be higher, negative, right? In that way, for the given reasons, enthalpy of the system is not the proper reason. The reason is entropy of the gas is decreasing. As entropy of the gas is decreasing, favoring factor will be the enthalpy. So favoring factor is enthalpy because entropy change is disfavoring. So the initiation for all these changes is entropy decreases for a gas. So like this, some questions will be more logical with respect to the concept. So let us see one more. So this is another question from thermochemistry. See, let us see. 2 moles of an ideal gas is expanded irreversibly and isothermally. Constant temperature is maintained at some 37 degrees Celsius, means 310 Kelvin, until its volume is doubled. So V1 is doubled to 2V1, right? Now, and these many kilojoules of heat is also absorbed from the surroundings. See, point to point we have to notice, very keen observation is required here. Heat is absorbed from the surroundings means, surroundings entropy decreases, no. So entropy change of surroundings will be negative. So immediately we have to go to that point. That comes only by practicing several questions. Okay, simply by 1 or 2 questions it won't come. Such models, several such models you have to practice. Okay, at least start from now onwards. Then delta S total is what? So let us see once. We have delta S total as delta S system plus delta S surroundings. Now delta S system for an ideal gas. Delta S system for an ideal gas can be expressed as NCV ln T2 by T1 plus NR ln V2 by V1. This is the basic equation. If it is with respect to heat capacity at constant pressure, NCP ln T2 by T1 plus NR ln P2 by P1. Okay, that's a different case. Now, at constant temperature, isothermal process, no, at constant temperature, this T1 and T2 will be same. Then delta S system can be given as NR ln V2 by V1. That equals to, it is 2 moles of an ideal gas into 8.314 into ln, it is double, no, ln 2. Ln 2 means 0.3010, whose product is 11.52 joule per Kelvin. 11.52 joule per Kelvin. Now, see, 11.52 joule per Kelvin. This is the value. Now, what is the formula to calculate enthalpy of surroundings? Enthalpy of surroundings can be calculated as minus delta H by T of the system by T. Minus delta H of the system. What is delta H of the system? Absorbed. It is minus of 3.41. It is kilojoules into 10 power 3 joules over temperature is 310 Kelvin. 310 Kelvin will be minus 11 joule per Kelvin. Minus 11 joule per Kelvin on division. Now, see, it is 31 again, another 31 is there. So 11 joule per Kelvin. Now delta S total can be given as 11.52 minus 11 joule per Kelvin. It is 0.52 joule per Kelvin. So which option is suitable for this? Plus 0.52, option B. So this is one numerical. So observe the cases. See, for each case I am giving one question. So we cannot discuss bulk of numericals in such video sessions, right? So specific models, how to understand the question and how to proceed, I am explaining. So do practice several such questions and then raise your doubts. Okay, and let us see another question. See another numerical from this entropy concept. See, we have entropy change involved in isothermal reversible expansion. Isothermal. Actually, entropy change of a system for an ideal gas. It is for an ideal gas. For an ideal gas can be given as NCV ln T2 by T1 plus NR ln V2 by V1. As it is an isothermal system, T1, T2 will be same. So entropy change of system for an ideal gas is given as, it is ln, no, ln to the base E. Convert it into logarithm to the base 10. It will be 2.303 NR log V2 by V1. Now we know the values. 2.303 into how many moles? It is 2 moles into 8.314 joules. Log V2 is 100 and V1 is 10. 100 by 10 log 10, it is 1. So on taking the product, it is around 4.6 into 8 4's 32 something. So 4.6 means 5, 5 8's 40, near to 40. So near to 40 but won't exceed 40. So it will be 38.3 joule per mole per Kelvin. Sometimes we have to come to an approximation in this way to save time. So this is one model of a numerical. Let us see one more question. So this is another question based on the relation between entropy change and enthalpy change. Entropy change and enthalpy change. Let us see what's the relation. Entropy change is given as enthalpy by T. Delta S is equal to delta H by T. It is vaporization, no. Entropy increases. During vaporization, entropy increases. So entropy change is positive. Got it? Now, what is this? T stands for boiling temperature. So we need to find out this boiling temperature as a delta H over delta S. That equals to what is delta H given? Enthalpy of vaporization is given as plus 30 kilojoules means 1000 joules over delta S. Entropy of vaporization is given as 75. On simplification, we will get it as 400 joules. So 400 Kelvin. Because this is joule per mole, this is per mole per Kelvin. That Kelvin will be left. So this is one simple numerical on this relation. Just to specify this relation and to remind you this relation, I had given this numerical. Let us see one more numerical. So this is another question which is based on Gibbs energy change or free energy change. See, determine the standard free energy change for the following reaction at some particular temperature. Is the equation given is N2 plus 3H2, which is at equilibrium with 2 moles of ammonia. Means for this equation we have to find standard free energy change. Another mistake usually that is possible in the examination hall, that is students will be in a mode of finding enthalpy change for 1 mole of ammonia, because they will confuse you by giving the values per mole. See here, it is given as kilojoules per mole. By looking at that value, they will find it for 1 mole of ammonia, but in the question it is specified, determine the standard free energy change for the following reaction. It is not per mole of ammonia. See, for the total reaction, they asked us to find it out. Now, how to find this? N2 plus 3H2, which is at equilibrium with 2 moles of ammonia, gas as well as gas. Now, standard Gibbs energy change can be given as Gibbs energy change of products minus that of reactants. Energy change of products means 2 times of delta G naught of ammonia minus Gibbs energy change of products, that is delta G naught of nitrogen plus 3 times of delta G naught of hydrogen. Right? Now what is standard Gibbs energy change of this one ammonia? It is 2 into minus 44.44 minus of, for nitrogen it is 0 and for hydrogen also it is 0. See, for hydrogen it is 0, nitrogen, hydrogen and ammonia, nitrogen, hydrogen and ammonia, it is minus 16.66, minus 16.66. So this is 0 plus 0. Option will be 16 to 32, approximately minus 33.32 kilojoules. Right? To be aware of this relation, I had given one question on Gibbs energy change. So let us see one more question on the same relation. Right? So let's have one more numerical on Gibbs energy or free energy concept. That is, we have delta G equals to delta G naught plus RT ln Kc, right, at equilibrium, or delta G equals to delta G naught plus 2.303 RT log Kc. This is the relation between Gibbs energy and standard Gibbs energy change. Now, for the following reaction which is at equilibrium, it is found that Kc value is 10 power minus 3. It is found that Kc value is 10 power minus 3. Therefore, delta G and delta G naught of the reaction at a given temperature will be at equilibrium. Gibbs energy change will be 0. At equilibrium, all measurable parameters remains constant. Even G also remains constant. So, change in Gibbs energy will be 0. Then delta G naught can be expressed as minus 2.303 RT log Kc. That equals to minus 2.303 into 8.314 joules into 300 into log 10 power minus 3, right? Log 10 power minus 3. So this is plus 3, right? This is plus 3. Then log 10 power 3. Log 10 power 3. Any other values are given? So we can find it out directly. Now on substitution, it will be minus 2.303 into 8.314 into, it is 3 into 300. Options are given in kilojoules, right? So this is joules now, into 10 power minus 3. Into 10 power minus 3. Actually, joule can be converted into 10 power minus 3 kilojoules, as options are given in kilojoules. Now, the product will be approximation. See, we have to come to an approximation. This is 900 into 10 power minus 3, 0.9. 0.9 means nearly 1. So, 8 into 2, 16. Minus 16 something. Where is that minus 16? So, minus 17.23. So, approximation actually. So, it is minus 17.23 kilojoules. Delta G is 0 and delta G naught is minus 17.23. So, in which option these values can be noticed? 0 and minus 17.23. It is option C. Right? Now, let's take one more numerical. Right? Let's have one more numerical. Standard entropy of the reactants and products for the given reaction. Delta H of the system, total delta H of the process is minus 30 kilojoules. Now, entropy change of the process, total entropy change of the process can be given as entropy of products minus entropy of half x2 and entropy of 3 by 2 y2. So, xy3 entropy change is 50 minus half of x2 value, half of entropy of x2. Entropy of x2 is 60, half of 60 is 30 and 3 by 2 of entropy of y2 it is 40. So it is 30 plus 60, right? 90. 50 minus 90 minus 40 joule per Kelvin. Minus 40 joule per Kelvin. Now, at equilibrium, it is at equilibrium, it should be at equilibrium. Delta G, as delta G is 0, okay, as delta G is 0, from this equation delta G equals to delta H minus T delta S, this is 0, so delta H equals to T delta S. Delta H is given as minus 30 kilojoules, minus 30 into 10 power 3 equals to temperature into minus 40 joules. So temperature is how much it is? Minus 3 by 4 into 10 power 3. 0.75 into 1000. 700. Minus will be cancelled. No, this is minus, this is minus. So 750 Kelvin. So these are some numericals from thermochemistry, right?